Well, hello, class. We're going to look at the first half of the homework assignments from lesson 2.2.2. I think it's questions 58 through 62. The first question references the big race, and this is heat number 3. Barbara, Mark, and Carlos participated in the third heat of the big race. Barbara thought she could win with a 3-meter head start, even though she only pedaled 3 meters every 2 seconds. Mark began at a steady line. He began at the starting line and finished the 20-meter race in 5 seconds. Meanwhile, Carlos rode his tricycle, so his distance y from the starting line in meters could be represented by the equation y equals 5 halves x plus 1, where x represents time in seconds. Alright, so there's 3 participants in this race, and the first question we're asked is, what is the independent variable? What's fortunate about that question is they really just kind of spelled out what the variables do represent, right? So we know that y is the distance we are from the starting line, and x, right, is the time, represents time in seconds that we're traveling. So we've got distance from starting line and time, and in this situation we would say that time is definitely the independent variable, and y, how far you are from the starting line, depends on how much time is elapsed. So I would say y is the dependent variable. So the distance I am from the starting line depends on, it's dependent, and it depends on x, which is how much time is elapsed, and x is the independent variable. Part B says using the given information, graph the lines for Barbara, Mark, and Carlos on the same set of axes. Who won the 20-meter race and who will advance to the final race? So let's go back to the clues here. We know Barbara has a 3-meter head start, and as we discussed in class, if you've got a 3-meter head start, that means that you have got to you're away from the starting line when time is 0. So this little dot right here, I'll do this color for Barbara, represents the fact that she is 3 meters away from the starting line when the race begins, right, at time 0. And it says that she pedals 3 meters every 2 seconds. So if I was to do this, here's 1, 2, 3 meters, right? That's 3, 4, 5, 6 meters in 2 seconds. And then for this scale, I'm going up 1 and 1.5 for every 2 seconds. So these values give me a nice look at Barbara's progress. Let me grab the ruler tool here and just line this up. Probably I should zoom out. Oh, that's going to be difficult. Zoom out, and then I'm just going to attempt to sketch her graph. So this is Barbara, and I can see that she's passing. I can see this where she's reaching this line up here. Y is 20, right? That represents the finish line. So I could graph that maybe in this. I'll just kind of make it darker in this white line. So that is the finish line at Y is 20. Okay, the next participant we had in the raid was Mark, and Mark began at the starting line and finished the 20-meter race in 5 seconds. So if I was to do that, there's 2 points we know about Mark, and we'll use green for him. He began at the origin, right? No head start for Mark. He started at 0, 0, and he finished the 20-meter race in 5 seconds. Well, here is 4 and 6, so right in between 4 and 6 is 5, and we're just going to follow that line up and go ahead and put the finish line right here for Mark. So this is the line that represents Mark's progress, starting at the origin and finishing in 5 seconds. And then the final racer we have is Carlos. Carlos rode his tricycle so that his distance, y, from the starting line in meters could be represented by this equation. So interesting, they've given me very different information for each racer here. Carlos does have a 1 meter head start. We can see that because his equation has this +1, and he's going up 5/2. So if he began here with a 1 meter head start, every what was it, +2, every every 2 seconds he's going to increase by 5 meters. So let's go ahead and go up 1, 2, 3, 4, 5, and then that's 2 seconds. So he does go through this point, which is a point Barbara went through. She was 6 meters from the starting line at 2 seconds, and he is also 6 meters from the starting line at 2 seconds. And then again up 5. That's 1, 2, 3, 4, 5, and then over 2 seconds. And I think from those 3 points, that should be more than adequate for us to graph Carlos. Okay, so I've created this additional representation, right, of the entire race. They gave us the one. Oh, they gave us the one representation. Oh, that line is there. They gave us some information, and we turned all of that into a graphical representation of the situation. And I can see my winners in this order. The first person that crossed the line was the green line. Would have been nice if I would have created a scale here, but that green line was Mark. So it looks like Mark won, followed by Carlos. Oops, Carlos, and then Barbra. So those are our racers 1, 2, 3. So yes, we definitely created a nice graph for all 3 of those, and that's up there. Next it says, write equations that describe Barbra's and Mark's motion. Okay, so we were given the fact that Barbra had a head start of 3 meters, so we know her y-intercept, and we can see it there, is at 3. And they also told us that she traveled 3 meters every 2 seconds, so we've got her slope also. So for Barbra, we'll write this equation: y equals 3 meters every 2 seconds. So y, the distance from the starting line, increases 3 meters every single time x increases by 2. So there's my slope ratio, change in y over change in x. I multiply that by x, and then I'm going to add to that the fact that she received it was a 3 meter head start? Yes, she received a 3 meter head start. All right, our next racer was Carlos, and oh, I didn't write Mark's equation, right? We got Carlos's equation. Let's write Mark's equation. So Mark went through the origin, right? So he went through the point 0, 0. So we know his y-intercept is nothing. It's 0. So we'll say his equation was y equals, and I think Mark traveled. Actually, we don't know his rate, do we? We don't have his rate down. Well, I know that he traveled 20 meters in 5 seconds, right? Because he finished the race. So I can write his rate that way. He traveled 20 meters, the entire length of the race, in 5 seconds. And I can reduce that rate to 4 meters per 1 second. So his rate is 4 meters per second. So I'll write 4x. And then it is plus 0. I don't need to write the plus 0, but it's just 4x. So this is Mark. So I've got an equation for Barbra, and I've got an equation for Mark. Next, how fast did Carlos pedal? Write your answer as a unit rate. So Carlos, we were told, traveled 5 meters in 2 seconds. This is not a unit rate, 5 meters in 2 seconds. That's a ratio. But if I wanted to write that as a unit rate, 5 divided by 2 is 2.5. So he traveled 2.5 meters per 1 second, right? So that's what a unit rate is. It's meters per a single second. So every single second that passed, he was traveling another 2.5 meters. And then when did Carlos pass Barbra? Confirm your answer algebraically. Well, when I look at it on the graph, we mentioned this when we were plotting it, right here. At 2 seconds, they are both 6 meters from the starting line. That's the location of that point. Now that's me looking at the graph and kind of deducing where that happens. If I want to confirm it algebraically, I want to look at two equations, right? I want to look at Barbra's equation, which was y equals 3/2 x plus 3, and then Carlos' equation, which they gave to us. Carlos was 5/2 x plus 1, y equals 5/2 x plus 1. And I believe that when we put 2 seconds into each of these, we're going to get the same distance from the starting line, because that's what y is. And if I say 4x equals 2 seconds, this equation, right, if this is 2, I've got, that becomes 3/2 times 2, which is just 3. So this becomes 3 plus 3, which is 6. So Barbra's distance from the starting line is 6 meters. And for Carlos, when I put 2 in for x, this becomes a 5, and 5 plus 1 is also 6. So his distance from the starting line is also 6 meters. So at in 2 seconds into the race, they are right side by side. It is Carlo that's passing because Carlo was behind Barbra, but after 2 seconds, Carlos is in front of Barbra. All right, let's move on to question 59. 59 says, which of the expressions below are equivalent to 16x to the 8th? Let me write this down here, 16x to the 8th power. Well, if I kind of simplify these, right, this, if you'll notice, what's being squared is 16x to the 4th, which means that there's two factors of 16, right? It's 16x to the 4th times another 16x to the 4th. And if I wrote that down, that would be 16 squared x to the 8th. And 16 squared is much larger than 16. So A is not equivalent to 16x to the 8th. If I look at B, I can see there's four things that are being multiplied, right? Well, there's an 8, and then there's 2 factors of x, and then there's a 2, and there's an additional 6 factors of x. 8 times 2 is 16, and 8 factors of x times 6 more factors of x gives me a total of 8 factors of x. So this is 16x to the 8th. This is definitely equivalent. Let's look at C, and we're going to raise something to the 4th power. So this is going to be 2, and I can write out 4 copies of this, right? Or I can say, hey, I'm raising a product to a power, right? You can see that this 2 and the x squared are being multiplied. There's going to be 4 identical copies of that. And if I wrote them all out, I would end up observing, oh, I've got 4 factors of 2. There's a 2, 2, 2, 2, 2 to the 4th power. And then I've got 4 sets of x squared, x to the 4th, x to the 6th. That would make x to the 8th power. Well, 2 to the 4th power, 2 times 2 is 4, times 2 is 8. Times 2 is 16, right? So 2 times 2 is 4, that's 8, and that's 16. So this is 16x to the 8th power also. So this is also equivalent. The next one, I'm going to square 4x to the 4th. So to square that, right, I'm going to have 2 factors of 4, that's 4, 4, and then I'm going to have 2 of these x to the 4th power. X to the 4th times x to the 4th would be x to the 8th. And yeah, when you square 4, you do get 16, so this is 16x to the 8th power. So this is yet another one. So B, C, and D are all equivalent to 16x to the 4th. Let's look at E. So on E, I have 4 identical copies of this. So if I wrote it out, and I will, it's 2x to the 4th times another 2x to the 4th times another 2x to the 4th, and then one more of them, 2x to the 4th. And I can see this shortcut here, right? When I have 2 to the 4th power, I end up with 4 factors of 2. And as we've already seen, 2 times 2 is 4, times 2 is 8, times 2 is 16. So 2 to the 4th is 16. But look at all these factors of x that I have, right? There's 4, 8, 12. There are 16 factors of x. So this is of 16 factors of x. So this is x to the 16th power. So this, right, 16x to the 16th power is not equivalent. Not equivalent. And then our final one, whoa, very interesting. Um, very interesting. I, I don't want to use a giant one to get rid of this negative exponent. I'm not going to do that. But I am going to observe that I am raising a product to a power, right? So I have two things. I have 1/16 and I have x to the negative eighth. They're both being raised to the power of -1. So what I can do is raise each of them individually to the negative first power. So that means that this becomes 1/16. That's going to be raised to the negative first power. And then I have x to the negative eighth, and this is going to be raised also to the -1 power. So we have this rule, right? If you have two factors, and be careful, these are factors. There are things that are being multiplied together to produce a product. But if you have two factors being raised to a particular power, something that's equivalent to that is you can raise each one of those factors individually to the power. So this is equivalent to a to the c times b to the c. But please listen and hear what I'm saying. These are factors being raised to a power. Please don't overgeneralize and misapply this somewhere else. And then, again, this just flies back to the definition of what exponents mean. So let's take a look at these. So the one part, right, I'm going to just rewrite this and leave it alone for now. So we'll talk about this next. But I've got 1/16, and I'm raising that to the -1 power. But then I have this x to the negative eighth to the negative first. Well, I know when I raise a power to a power, I can just multiply. So this is x to the positive eighth power. Now, if I wanted to see that in maybe a little bit more illuminating way, I could say, look, this is x to the negative eighth, and I'm going to get rid of the, no, I don't think I want to do that. I'm going to leave this where it's at. So the last part here is, how do I deal with 1/16 to the negative first power? Maybe we should spend a little bit of time just looking at this. So if I wanted to get rid of the negative exponent, I could choose to multiply this by the number 1. And the number 1 I would multiply it by would be 1/16 to the first over 1/16 to the first power. In my numerator, I've got 1/16 to the negative first times 1/16 to the positive first, which is 1/16 to the 0 power, right, which just equals 1. So this numerator just becomes a nice little well-behaved number 1. My denominator becomes 1/16. And we were practicing some rational expressions last week in another homework set. And we were talking about the fact that, hey, if you're dividing by a fraction, well, there's a lot of ways we could do it. We could multiply by the reciprocal. The other thing we know that is, by definition, right, this 1/16 is the same thing as 16 to the -1. It is. It is. So I could now clear that negative exponent and just get the fact that that's just the number 16. There's probably an easier way I could look at that too. If I start with the original 16 to the -1, if I use the fact that a to the -1 is the same thing as the reciprocal of a, I could just say that 1/16 to the negative first power is the same thing as the reciprocal of 1/16, so it's just the number 16. Anyways, probably playing around with this longer than I need to. This 1/16 to the negative first power is 16, and then we've got this x raised to the 8th power. So this is part F, and it is the same as well. So we have quite a few of them, right? It turns out that B, C, D, and F, I use square boxes, and F were all equivalent to 16 times x to the 8th power. Let's move on to question 60. It says, for a certain function, if you give it a, it gives you back 51. Okay, let's say that again. For a certain function, the output when you put in a, and I don't know what a is, it doesn't matter to me, but if I put in the value a, the function gives me back 51. So listen to how I'm reading this, talking about it, right? This f of a always means the output of a function when you put in the value a. Well, when I put in a, I get 51. So that means that this is the number 51. That means this is the number 51. And that means this is the number 51. So my answers are going to be, and you could do the arithmetic, just 51 minus 8. This is going to be 1/2 times 51. And this is going to be 1/2 times 51. And then we're going to decrease that by 8 units. So again, just notationally, right, f of a, when we see that, we're thinking, oh, f of a, that's the output, right, when you put a into the function f. And they're telling me that the output when you put a into the function f is 51, right? The output when I put in a is the number 51 for a certain function. Not all functions, but this particular function, f. You give it a, it gives you 51. We're on to question 61. 61 says the equation, write the equation for the following tile pattern. So this is going to be one of those places where I would like to look at a different representation. So they don't tell me figure 0 or figure 1, but I have figures 2, 3, and 4. Figure 2 has 4, 5, 6, 7 tiles, I believe, right? 1, 2, 3, 4, 5, 6, 7. And figure 3, it looks like all it did was it just increased by these two. These are the new tiles, so it went up by 2. So 7, 8, 9, 9, 10, 11. So I can see two things, right? I can see as if x is the figure number and y is the number of tile patterns, when x increases by 1, the number of tiles is increasing by 2. Right? So when that goes up by 1, this goes up by 2. So that's the unit rate, right? Every time, when it goes up by 1, every time x increases by 1, y increases by 2. So I know my unit rate or my slope, or I know a change in y, right? Y just changed by 2 divided by the change in x. So I know my slope. The thing that I don't know is I do not know my y-intercept, but it's pretty easy to figure that out. I'm just going to move backwards. So 7 minus 2 would give me 5, and then 5 minus 2 would give me 3. So 3, 4, 5, 5, 6, 7. So now I know figure 0 would have 3 tiles in it, and I can write the equation. If y is the number of tiles, right, y equals 2 times the figure number and then plus 3 starting tiles. So if x and y are defined properly, that would be the equation for this situation. Then our last problem we're going to do right now is question 62, and it says graph the equation y equals negative 2x plus 9. Don't need to look at this, but I will anyways. If I put 0 into that function, it's going to give me plus 9. If I put 1 into that function, it's going to go down by 2, right? I'm going to decrease 2 by 2 each time x goes up by 1. So when x increases by 1, y will decrease by 2, so that should be 7, right? 8, 9, 8, 7. So I can see here two things. I can see my y-intercept. I know where I'm starting is 0, 9, and I know that my slope pattern is my change in y is negative 2, my change in x is 1. So if I wanted to graph that, here is a beautiful y-intercept at 9, and then I'll go down 2 over 1, down 2 over 1, down 2 over 1. So this is my function, and I can line up the ruler and just quickly draw the line that goes through those. There we go. So, ooh, that was an awful line. That was just terrible. Let me get rid of that, and you too. And now there's a better line. There we go. So I like to include these arrows right on the top and bottom that indicates that this is continuous. It keeps going. And I'm going to write right here, this is y equals negative 2x plus 9. All right, so there is a second half to this lesson. We'll finish up section 222 tomorrow in class, and then we'll look at questions 63 to the end in another video. Have a good day, class. I'll see you in class soon.